All right, today we're jumping into a full-on chemical investigation. We're looking at one of the most interesting families on the entire periodic table, the halogens. We're going to uncover their family secrets, follow the clues in their behavior, and really solve the mystery of what makes them so reactive and why that reactivity changes.
So here's how we're going to crack this case. First, we'll meet the family. Then we'll hunt for clues in their physical properties. After that, we'll look at the hard evidence of their reactivity, stage a little head-to-head competition, and finally, we'll get to the big reveal, the science behind it all, before wrapping up with the key takeaway.
Okay, let's dive right in. Our investigation starts by getting to know our subjects, the chemical family we call the halogens. So you can find the halogens all hanging out together in group 7. That's that vertical column way over on the right-hand side of the periodic table. Now, they're all reactive nonmetals, which is our first hint that this is a pretty lively bunch. And you know them better than you think. Chlorine, for instance, is the halogen that keeps swimming pools clean. Now, their family name, halogen, is really cool. It literally means salt-producing. And that's because it's what they do best. When a halogen like chlorine gets together with a metal like sodium, they react to form sodium chloride, which you and I know as just plain old table salt. Same goes for iodine, another halogen you've probably used in antiseptics. And here it is, the secret that really makes them a family. Every single halogen atom has exactly 7 electrons in its outer shell. You can think of it like they're all just one puzzle piece away from being complete. And their entire chemical identity is driven by one thing, finding and grabbing that one last electron. That shared goal, that obsession, that's the engine behind all their reactivity. Okay, so let's move on to our first set of clues. You know, just by looking at the halogens, we can spot some really clear, really predictable patterns as we go down the group. Just look at this. The pattern is right there in front of us. At the top, you've got chlorine, which is a pale green gas. Go down one step and you hit bromine, a brown liquid. And below that, iodine is this deep purple-black solid. The trend is unmistakable. As you go down the group, the colors get darker and they get denser, going from a gas to a liquid to a solid. So seeing that trend leads to a pretty natural question. The fact that they go from gas to liquid to solid means their boiling points have to be going up. But why? Figuring this out is the next step in our investigation. And the reason is actually pretty logical. See, as you go down the group, the molecules just get bigger. And because they're bigger, the forces of attraction between them get stronger. We call these intermolecular forces, and they act like little invisible magnets pulling all the molecules together. So to break those stronger forces apart and get the substance to boil, you just need to put in more energy. It's a really neat and tidy explanation. So their physical properties follow a really clear pattern. But does that same predictability apply to how they behave chemically? This is really the heart of our investigation. It's time to look at the most important evidence, how their reactivity changes. Okay, check this out. This shows what happens when they react with hot iron wool. Chlorine, it makes the iron burn vigorously. Bromine makes it burn quickly, but you can see it's a little less intense, and by the time we get down to iodine, the reaction is just slow. So there it is, our first piece of hard evidence. It really looks like reactivity goes down as we move down the group. And if you thought that was clear, this next piece of evidence is even more dramatic. Just look at how they react with hydrogen. Fluorine, sitting right at the top, explodes even in the cold and the dark. That's the same element we use in toothpaste to protect our teeth, by the way. Chlorine needs a little push from sunlight to explode. Bromine needs to actually be lit on fire. And iodine, it barely reacts, even when you heat it up. The trend is, well, it's undeniable. All right, the evidence is all pointing in one direction, but to be absolutely sure, we need to confirm it. Let's put these halogens head-to-head in a direct competition. It's time to figure out once and for all who's the most reactive. Welcome to the displacement showdown. The rules of this competition are super simple. The more reactive halogen always wins. It will literally kick a less reactive halogen out of its solution and take its place. It's a pure test of chemical strength, plain and simple. So let's look at the scoreboard. When we add chlorine to the other solutions, it is the undisputed champion. It kicks out both bromine and iodine. No contest. When we try bromine, it's strong enough to displace iodine. But what about poor iodine? When we add it to the others, nothing happens. It's just not strong enough to displace anyone. The results are in, and the verdict is crystal clear. The order of reactivity is chlorine is more reactive than bromine, which is more reactive than iodine. The showdown has officially confirmed our theory. So we've figured out what happens. We've seen the evidence pile up, but now we get to the most important question of all. Why? It's time to solve the mystery behind this trend. This is the big reveal. And it all comes back to this one crucial idea. Remember their family secret? That desperate need to gain one more electron? Well, that's everything. Their reactivity is just a measure of how easily they can attract and capture that final electron they're all looking for. Let's just walk through the logic here, step by step. As you go down group 7, the atoms get bigger because they have more layers, more electron shells. This means that outer shell gets further and further away from the positively charged nucleus at the very center. Now, with all that extra distance, the pull from the nucleus on a new electron trying to join is just weaker. And if that pull is weaker, it's a lot harder to gain that new electron. So what does that mean? It means the halogen is, by definition, less reactive. It all fits together perfectly. Okay, let's bring it all home and consolidate everything we figured out in our investigation. We've followed the clues, we've analyzed the evidence, and we've uncovered the cause. Now it's your turn to be the scientist. So here's what you really need to lock in. First, every halogen in group 7 is driven by that need to gain one more electron. Second, their reactivity clearly and consistently decreases as you go down the group. And third, the reason for that is because the bigger atoms just have a weaker pull on that new electron they're trying to attract. And that brings us to our final challenge. Astatine is the halogen that sits right below iodine on the periodic table. So, based on everything we have just learned about this family's trend, here's a question for you. Will astatine be strong enough to displace iodine from a salt solution? The answer lies in the rules we've just uncovered.